Hello everyone, my name is Nicholas Wiley, and in today's transport video, what we're going to be doing is we're going to try and find out the maximum power that can be generated by a wind turbine. So what I have over here is I have our wind turbine. I think the first important thing before we get into power, as we do not have enough information to get there yet, is to simply just discuss our system. Now I'm going to go ahead and start us off with one fact. One fact that we know about this system is that our density is going to be constant throughout. This is going to be very key, as we're going to see later on in the video. But continuing on, another thing we know about this system is that we have some sort of fluid, which is going to be air or wind in this instance, is going to be flowing into our system, and it is going to pass through our entrance that has an area that we are going to denote as A1. In addition, we know that there's going to be wind flowing through a turbine, very obviously. And when we're talking about this, I'm not going to put the arrow up here. I'm actually going to put it down here. What we know is that there's going to be some sort of velocity of our fluid at B blades. At this point, I drew some dots here earlier. Just so we know that there's going to be air passing through those blades that's going to be generating that power that we are discussing, and we will find out later on in this video. In addition, we know that after it passes through the blades, it must exit at some exiting velocity V2, and the area cross-sectional area of our exit is going to be denoted as A2. So let's continue on with that. So now that we have all these pieces together, it's important to note that we are going to be in steady state throughout this process. What does that mean for us? That means that whatever air, wind, fluid, however you'd like to say it, I'll call it fluid, okay? Whatever fluid we have entering from at this point, A1, our entrance, must exit at our exit, which is going to be A2 denoted. So now that we understand that, well, do we understand that? I think that makes sense. So why is that important for us? It's important for us because the whole heart of this problem, before we jump into our power, is going to be discussing momentum and momentum balance. So for our system, we can start with the momentum conservation equation. What we're going to have is we're going to have the derivative of the mass of our system multiplied by the velocity of our system with respect to time. So the change in our mass of our system multiplied by the velocity of our system over time is going to be equal to the velocity into our system multiplied by the mass flow rate into our system minus the velocity out of our system multiplied by the mass flow rate out of our system plus any forces that may be generated or the opposite of generated, used up, any force that is generated. Okay, we'll just stick to that. Any force that is generated, we're going to say is going to be denoted as F force. Now, what can we do with this? Well, what do we know about our system? It's at steady state, which means that there's not going to be any mass of our system that is going to be changing over time. So this is simply going to become a zero for us due to steady state. In addition, we know that these two right here are going to be the same. The mass flow rate into our system is going to be the same as the mass flow rate out of our system, as I've discussed. So what we can go ahead and do with this is we can go ahead and simplify a little bit. So what I'm going to say is, in parentheses, our velocity in minus our velocity out multiplied by our mass flow rate plus our force is going to be equal to 0. Now we can further make this more simple for us, and we can put negative F on this side. And if we want, our velocity in is going to be denoted as V1, as I've discussed. So it's going to be V1 minus V2, which is the velocity of our fluid that is going to be exiting our turbine. So now what we're at is we have negative F, negative force is equal to velocity, the velocity entering minus the velocity velocity entering minus the velocity exiting multiplied by our mass flow rate. Now for this problem, we don't know our mass flow rate. So what we're actually going to do is we're going to figure out a different way to express this mass flow rate. Now what do we know about mass flow rate? This is going to be in kilograms per second. What can we do with that? We know something else that is going to be in seconds for us, a different rate, and that's going to be our volumetric flow rate, which is going to be Q. Q is going to be meters cubed per second. So what we can do is we can multiply that by our density, which is going to be in, already forgetting, it's going to be kilograms per meter cubed. Quick cancellation, that'll give us, just to show you, that'll give us kilograms per second. So now that we have that, we actually can move that a little bit further. What do we know about Q, our mass, or our volumetric flow rate? We know that it's going to be equal to our density. Here, let me just do some units while I do this. So we know that we have our density, and we also know that it's going to be equal to our velocity, meters per second. We also have kilograms per meter cubed, and then we're going to need something else. We're going to need to get meters squared in the numerator. How are we going to do that? Well, we are going to use area A. Now, the next part is pretty important for us. We need to decide which area we are going to be talking about in this case. Well, luckily for us, we have a problem description. We're looking for the maximum power generated by the turbine itself. So what are we going to do? We're actually going to use V sub B and A sub B. Both points at this center of our turbine. Not the center of our turbine, but this area, the complex area in between the blades. So what I'm going to go ahead and do is I'm going to go ahead and make some substitutions. I'm going to move this up here to the top left corner, just to give us some more room to continue throughout before we start talking about power. But where we're at now, we have negative force is going to be equal to V1 minus V2 multiplied by rho velocity at B times the area at B. Now what we can go ahead and do is get into power. Alright, so now we're going to go ahead and talk about power. As you can see, I've cleared the board for us to make room for a lot of things that we're about to do, and hopefully we'll be able to drive this all the way to the end in this one quick take. So let's go ahead and do it. Talk about power. What is power? Denoted P. Power is, first definition, there's two definitions, is going to be a change in energy over time. For us, it's going to be kinetic energy. As we're talking about a moving turbine, we're talking about power that is going to be generated. So we're going to call that a change delta KE over time T. But we can't use time T. Why is that, Nick? Well, the whole point of this problem is that we're talking about flow through a turbine. So what we're going to use is we're going to use our mass flow rate term that we used before. So let's go ahead and do that. So what we're going to have to do is we're going to have to put our mass, it's our changing kinetic energy per unit mass, multiplied by our mass flow rate. Now we need to talk about the second definition, which is a little bit trickier than the first definition. The second definition is going to be that our power is going to be equal to our force multiplied by our velocity. Whatever velocity we may choose, whether it's the entrance, the exit, or the blades, which we are going to be using in this case. Nonetheless, let's go ahead and write that out. F multiplied by V. Now for us, and for this case specifically, I think this may apply in just about every single other case, this F is actually going to be negative. Now there's one way to think about this, which may be the most easy to try and think about, is that pretty much the force and the velocity are going to act in different directions to create power. I try to think about it as if the velocity is going to be traveling through the blades, and it's also going to be turning that turbine at the same time, which is why you're in turn going to have basically a force acting in the opposite direction. And yeah, I don't know if that really makes sense, but I think the best way to think about it is that they're clashing together. They're going in opposite directions. Not really sure about how the directions would look, what this really looks like. But for our sake, let's just keep it simple. I'm going to tell you that our power is going to, for our second definition, is going to be equal to negative force times velocity. Now, what do we know about our change in kinetic energy? Well, that's pretty simple for us. We know that V1 minus V2 squared, both squared, V1 squared minus V2 squared, over 2, that's going to be our change in kinetic energy. Now what do we know? We know our mass flow rate. Now what did we use before? I believe, so we have kilograms per second. Sometimes when I can't figure out exactly what I'm to do, I like to think about units. We have kilograms per second. How are we going to get there? I believe it was rho for our density, which is simply just kilograms per meter cubed, multiplied by our velocity at our blades, so in kilograms per second. Our velocity at our blades, which is going to be meters per second. Oh, yes. And then we're going to be multiplied by our area at B. So that is going to be our mass flow rate. going to be equal to, just leave the eraser there. It's going to be equal to negative f, which, look at this. This is perfect for us. This is why we did what we did before with the momentum balance and set negative f on the left side, so that we can substitute this in, and we can't remember to multiply by this v right here. So let's just go ahead and do this. So let's put in our negative f. So we have v1 minus v2 multiplied by rho vb squared. We're going to say that this is b for us, because we're multiplying this negative f, by vb. So it's going to be vb squared multiplied by a b. Man, I'm using too much room right now. We might have to shrink it a little bit, just so I don't have to erase a bunch of things. Either way, though, looking at this, what can we do? We can do a couple of cancellations. We can cancel out our density. We have 1 vb, we have 2. Let's get rid of one of these and get rid of our squared on this side. Let's get rid of our area at b on both sides. Oh, did I already get... I think I already got rid of my density there. So this is what we're left with now. As you can see, we can actually make an equation for our velocity at our blades. So what we're going to go ahead and do is I'm actually going to forget about this for now. Excuse me. So what we're going to have is we're actually going to end up with 1/2, and I'm going to make a little, I'm going to divide by v1 minus v2. 2's already here, so we're going to end up with is v1 squared minus v2 squared over v1 minus v2. And all of this is going to be equal to v sub b. Go ahead and get rid of this now for you. Interestingly enough, what we can do, I'll just draw a quick arrow over here. How do we decompose this right here? This is simply going to be v1 plus v2, v1 minus v2. Thinking about that, we can cancel, and what we're going to be left with is 1/2 of v1 plus v2 is going to be equal to our velocity at the blades. Now, what does this mean? I'll draw the turbine real quick. That was really not good. That means that the entrance velocity and the exit velocity, that means that the velocity here in between these blades is simply just the average of our entrance and exit velocity, which is actually kind of funny to think about. Is it seems pretty simple, but now what we've done is we've proved it algebraically through momentum balance and power definitions. So something is, maybe even somebody could guess that, well, maybe it's the average since it's in the middle. Well, it is actually, which is kind of interesting to think about, is that it is the average. I just thought that was pretty interesting when reviewing the content and going through this. Either way, now that we've gotten this far, what we're going to want to do is we're going to want to somehow figure out, at Eraser Man, we're going to try and figure out what the maximum power is that we can achieve, given that we have the perfect situation with steady state, nothing being exiting, things that are entering the entrance, exit 100% of the time. Either way, I'm actually going to write this over here. Just so that we remember. Now that we have these up here, let's go ahead and try and create an equation for this. So we're going to have that the maximum power is going to be equal to our change in kinetic energy, which again was the V1 squared minus V2 squared over 2. That's our change in kinetic energy. And then what we're going to have to do is we're going to have to multiply by our rho. And then we also have that VB term. Well, we figured out what VB is. So what we're going to go ahead and do is we're going to go ahead and insert this piece right here. I'll put brackets around it so we understand. 1/2 V1 plus V2 AB. Now you can see what I was talking about. Actually, I don't know if I said it in this take. But what we're going to end up with now is we're going to end up with a quadnomial, I believe. I don't really know the term. It's a polynomial either way. Nonetheless, and I'll actually get rid of some of this for now. So now look at this. We have a pretty nice equation, and this is going to be our maximum power. So let's go ahead and do a little bit of reorganization. So we have a 1/2 of 1/2. So I'm going to make this that power is going to be equal to 1/4. So I'm just going to put a 4 on the bottom. We're going to want to pull out our constants for this, which are AB and area at our blades, the strange area that we're going to have. So rho multiplied by the area at our blades. So cancel as we go. And then this is going to be the fun part. We have V1 squared minus V2 squared multiplied by V1 plus V2. Okay, and I'm actually going to keep erasing as we go, so just you can take notes, pause the video whenever. So I'm going to go ahead and erase this. We're going to put it above just so we have a little bit more room to mess around at the bottom. Either way, now that we have this, we can go ahead and expand. We can do the FOIL that they taught us back when we were kids. So let's hopefully do this right. Let's hopefully not flub it up, as they say. So what we're going to do is we're going to take the first term. So we're going to have V1 cubed. Okay, we have V1 cubed. Also, what we're going to do is we're also going to refer to this as just C, a constant. Because for our sake, this does not matter what this ratio may be. What we're focused on is the velocity, the power itself. We can just figure out what the constant is. We're looking for the ratio of the velocities that's going to give us the maximum power in our wind-powered, fluid-powered turbine. So we have the V1 cubed, and then we're going to do V1 squared times V2. So plus V1 squared multiplied by V2. Now we have our second term. We're going to go second term, first term, minus V1 V2 squared. Okay. And then we are also going to do... Oh, second and second. Sorry, I got lost for a second. Minus V2 cubed. Last term, or second term, second term. And this is going to be equal to our power. Okay, this is looking pretty good. Now we have this here. What are we going to be able to do with that? We could maybe put this into something to figure out what our roots may be for that. But we're going to take a little bit different of an approach. I don't really want to do that yet. The first thing we want to do is we want to find, I can erase this for now. Because we're going to, just remember that we are going to call this constant. This is going to be our C term that we're going to be multiplying by after we get that ratio. But the ratio is the most important part for us right now. So let's go ahead and erase this. Now that we're here, let's think about this. How are we going to find the maximum? How do you find maximums? Well, maximum always occurs, yes, a maximum always occurs when the slope of something is 0. Think about a parabola. The minimum is at the, when the derivative is equal to 0. So what we're going to want to do, actually, is we're going to want to take the derivative of this, both sides, and set it equal to 0. So let's go ahead and do that. So we're going to have the derivative of our power with respect to time, yes, is going to be equal to C multiplied by the derivative of this, which we are going to call, actually, before I do that, I actually did miss a step here. Let's take a step back for a second. Now, looking at this, what can we do? We have so many different things that are being done here. Not really done, but you know what I mean. There's a lot of things going on. There's a lot of V1, V2s, cubed, squared, to the first power. So what we're actually going to do with this is, let's try and think of a ratio R. What is this ratio R going to be? Let's say that R is going to be V2 over V1, right? If we look at this, that pretty much perfectly matches us what we need to do. Does that? Yes. Yes. That will work for us. It doesn't matter if we did V1 over V2. It just makes more sense to do V2 over V1. You could have done either one, but for me, it makes more sense to do V2 over V1. Now let's go ahead and do that. Let's rewrite this in accordance to our ratio. And how are we going to do that? All we have to do is we're just forget about these P's and C's for now. This is just in its own little world. We're not worried about that. We're worried about our polynomial. So what we're going to do is we're actually going to say that we are going to have V1 cubed out here. So what is this? This becomes 1 plus V2 over V1. We have the power of 2. Factor out that. You get a V1 on the bottom. Minus V1, V2 squared. Okay, so we have minus V2 squared over V1 squared. And then to end it off, we have V2 minus V2 cubed over V1 cubed. Now looking at this, look at our little ratio that we set up before. That's why this works perfectly. V2 over V1, that becomes R. This right here, what does that become? V2 squared over V1 squared, that becomes R squared. Now V2 cubed over V1 cubed, that becomes, you got it right. I know you did. All you at home, R cubed. Now look at that. Isn't that just beautiful? So now what we can go ahead and do is we can actually get into that derivative we were talking about. Let's take a derivative of power with respect to time. This is going to be equal to C, which is a constant, also with, yes, that's a constant. And then what we're going to do is we're going to want to take the derivative of this piece here. So let's just go ahead and do that. So I'll just remember this 1 plus R minus R, or let's just write it out. So we're going to have C, let's go ahead and do this. Derivative of 1 is 0, derivative of R is 1, minus 2R minus 3R squared. Is that, okay, so this is all looking good. Yes, okay, let's just get rid of this. I like keeping my board neat as we go, actually. Since we're in the home stretch, it'll be nice just to have the most important pieces on the board. So looking at this, as I said before, I completely got sidetracked and did the wrong thing. We need to have our derivative set to 0 because that's where maximums occur, especially for a binomial, of which we now have. Also, I got rid of the V1 cubed because we don't really care about what the values are for this. We're looking for the ratio of our, I guess, exit velocity over our entrance velocity. Trying to figure out what the perfect ratio is to find our maximum. And since Paul, yes, that is what we're going to do. Okay, so looking at this, what can we do? Let's see. So we're actually going to have 2 zeros for this because we need to factor this. Let's go ahead and try and factor this live. So it has to be negative 3R. Can't really have any, we can't like divide 3 by 2, like 1.5 times 2. We're just going to get a mess if we do that. So negative 3R, and the rest has to be 1s. So I have to figure out if this is positive or negative R plus R minus R. So let's think about this. Now we have negative 3R squared. We need a plus 1, so we actually need both of these to it's either plus plus or minus minus. So if you made this minus minus, this would be plus 3R minus R, wait, shoot. I believe it's plus 1. Negative 3R squared minus 3R plus R plus 1. So that'll give us minus 2R. Now what if we made this negative? I'm just trying to do this for my own sake. Would it be the same? Negative 3R plus 3R, minus R, so that would be the difference. Okay, so now we found this. A very important piece for us, as we've done for many, many years. When you have something like this, you can find both of the zeros when we were factoring as kids, whether it was x squared plus 2 plus 1, x squared plus 2 plus 1, and the zeros are negative 1. Either way, I'm getting too ahead of myself, or actually behind myself. Let's just go ahead and solve this. So if we solve for R over here, we get that R is equal to negative 1. Now what would that mean? That would mean that the velocity at 2, that would mean that the ratio would have to be negative 1. So that would mean that if it's entering at 5 meters per second, it would have to be exiting at negative 5 meters per second. So if you have 5 meters per second, and then you have an exit velocity of negative 5 meters per second, that would actually mean that it is going positive in the other direction. So your turbine would not be moving, and there's no way it could be maximum power. Let's make sure. I thought I wasn't recording. Either way. So since we know this ratio, now we know that this is not the piece that we need. So our answer is going to lie, our ratio is going to lie within this second piece. Now what is our answer going to be? Well, if we simply do some math, we know that 1/3 times 3 is 1, so we have -1 plus 1. That gives us our 0 that we need. So R is going to be equal to 1/3. And what does this mean? That means for a perfect system, a perfect fluid-powered turbine system, the ratio of the velocity entering and the velocity exiting, the velocity exiting and the velocity entering, for it to generate the most possible power, would need to have a ratio of 1/3. So that would mean, say, that wind could be entering at 3 meters per second, and that it would have to be exiting at 1 meter per second. Yeah, so that would be our ideal situation. For maximum power generation, we want the ratio between the exit velocity and the entrance velocity to be 1/3.